Hello, everyone. Before I welcome any of our guests, I'd just like to invite those who've not already done so to please subscribe to our Magnimind Academy YouTube channel, where we upload recorded sessions of these talks, and so you can watch them later. And please comment any questions or comments or thoughts in the comment section below, or just let us know what you think about today's talk. Now I'd like to welcome Dave DeCaprio, who will be speaking about practical machine learning for healthcare. At Magnimind, we really try to find speakers like this who can give a different perspective or new or more current information to go along with our data science education programs. These programs focus on the fundamental skills of data science, and they also will take you from just one skill or an entire career change into the industry. We're actually going to be launching 2 different one-on-one mentorship boot camps that will focus on data analysis or machine learning, and we're going to upgrade your skills with flexible project-based learning alongside our industry-leading mentors. Our goal at Magnimind is impacting as many careers as we can, and this is really just one way that we do so. I just saw a comment. Yes, this is recorded. It'll be on YouTube shortly after we end. Anyways, DeCaprio joins us with over 25 years of experience in the industry, taking on roles ranging from engineering to consultant to a CEO, and he currently works 2 different positions, one as the CEO of Scissor, a company that implements computer vision and analytics to help tennis players improve fast, and he is also the CTO of ClosedLoop.ai, which is a platform that brings AI into health, payers, and pharma. In this talk, DeCaprio will be focusing more on the second position, or the experience learned from that, where he'll be sharing many of the lessons he has learned in his own career in healthcare and what he has learned from his mistakes so that hopefully you'll not have to repeat them. We're very excited to have him, so please now give your full attention to Dave DeCaprio.
Right. Hello, everybody. Let me get my screen shared here. Perfect. Good. So, going to talk tonight about practical machine learning for healthcare. I know a lot of people talk about the nuts and bolts of building machine learning models and how to run certain libraries. I like to cover a lot of, what I've seen from having actually delivered predictive models, AI, machine learning into real environments that are used day to day over the last 15 years. And I think there's a lot of things you don't think of or learn about when they first teach you data science. You're very concerned with sort of getting the numbers right, but sort of fitting that into what does it take to actually use all this stuff to make somebody's life better. There's a lot of interesting challenges come with that. So that's kind of where this talk will focus. Give a little bit of background on me. I've done a lot of things in software engineering, computer science, machine learning, healthcare. Was on the Human Genome Project. That was kind of my start into what was called pattern detection back then, but then they called it machine learning, and now it's advanced into AI. But really, the fundamental things all kind of came back from there. So, as you said, I'm this Chief Technology Officer of ClosedLoop.ai. We're a data science platform for healthcare. So most of what I talk about today is the kind of stuff I do every day, day to day at my day job and what we help companies with. I'm not really going to talk a whole lot about the platform except when it's relevant to the particular story I'm telling. But this is what we do. So what I will talk about today is healthcare's $1 million challenge. I'll start with that. And then I want to talk a little bit about bias and fairness. That's a huge topic right now and a very important one, and I think important to address early. And then a little bit about communicating the accuracy of a predictive model. So once you've actually built something, how do you explain to somebody who's less technical or not a data science how to use it? And then I'll give you some of the things that work in healthcare. If you're actually a practitioner in healthcare, here's what I've found that works. And then a little surprise at the data science voodoo at the end. Some more stories I've had. So the $1 million healthcare challenge, this is actually quite literal. There is a $1 million challenge for healthcare that CMS, which is CMS is the Government Center for Medicare and Medicaid Services. So that's the federal government organization that runs Medicare. And they sponsored $1 million challenge it was announced in March of 2019. People could apply. There were 400 teams to apply. I was the leader of one of those teams. We were accepted into sort of the stage 1 competition. There were 25 teams selected to compete for this $1 million prize. And the goal is to use AI to predict unplanned hospital and SNF, which is skilled nursing facility admissions for Medicare beneficiaries. So basically take in Medicare data from Medicare and then predict who's going to go to the hospital, who's going to get sick. And we actively just completed our submission for that a couple of weeks ago. It was delayed because of COVID, and we will find out if we're a finalist in October of this year. So that's going on. I think it's always interesting to hear about these challenges. What's it like to be in the middle of one? So the first thing here is the data we're using. So as part of this challenge, we got access to healthcare claims data, which is actually one of the most common types of healthcare data. It's the billing data that's used. So if you've ever gotten a very long 10-page bill after you've gone to the doctor and it has all these lines with a bunch of incomprehensible codes and dollar amounts to it, that's the raw data that runs many of these models. The good news about claims data is that it's very standardized. Because it's used for billing, everybody uses it, and they use it in mostly a consistent way. The bad news is that it doesn't have maybe all the detail you want. As part of this project, we got access to some of this Medicare data. This is actually data you can purchase. So it's about $5,000 per year to purchase this data. You need to have a research plan. You can't just sort of download it from the net. But if you have a reasonable machine learning or other kind of research plan that you want to do around this data, you can have access to it. It's a 5% sample of nationwide Medicare beneficiaries, and it's all been anonymized. And there are some issues because it's been anonymized. Again, as a data scientist, I always want to go down to the bottom and know exactly what the data looks like. So what generates this data? So again, this is like the raw billing data that runs basically the whole healthcare industry in the US. There's a lot of bizarre details to how it's collected, but this is what a hospital sends to Aetna or United or Blue Cross in order to get paid. It has a lot of these numeric codes. So there are various coded things for drugs, diagnoses, procedures. And, we can use that to an advantage. If you understand how to use all those codes, those are a big deal. There's a lot of detail in the data, but it can be very useful. So the sort of ups and downs of this data, the biggest drawback is compared to sort of an electronic medical record, you don't really know a lot of the clinical details. You don't get the notes from the doctor. You don't get even the result of a test. Because it's billing data, you basically get, here's what the test was, and here's how much it cost, and here's why they did it. But they don't give you the actual result. It often, if you've ever dealt with medical bills, they take a long time to sort of work their way through the system. So there's delays in there. There is sort of gaming in the system where, because it's used for billing, people will bill things in a way that is favorable to them. But there are some very important things about this data. The main thing is it's very comprehensive. Generally, your insurance company is the only organization that knows everything that happens to you from a medical perspective. If you go to one hospital, get a treatment, and then you go to a doctor, all of those records don't necessarily get put together. Certainly in the US, there's no system that makes all that happen. So the billing records that your insurance company has is the most complete picture of what your health state is. They know the prescriptions you're taking. They know the doctors you've been to. They know any hospital you've been to. And so that ends up being very useful because you're getting a full picture on the patient. And it's also data that is well curated. Because this is the data that drives payment, it ends up being reasonably high quality data. If it wasn't, then people couldn't get paid on it. And it's also very standardized because people use it back and forth. And again, I talked about these coding systems in there. There are diagnoses. So diagnoses in healthcare, the standard classification is called ICD-10. There are actually 70,000 diagnosis codes that are used. So, there's all kinds of crazy diagnosis codes. These things get ridiculously specific, you know, running into a lamppost, second occurrence or something like that. That's an actual code. But it is very useful because you do get a very fine-grained view of what's going on with people's procedures is another thing. So diagnoses is what's the disease or the cause, what's wrong with you. Procedures is what actually happened. So what did the doctor do? An appendectomy, if the doctor removes your appendix. Appendicitis is the diagnosis, and appendectomy will be the procedure. And there are other coding systems for this. And then drugs. There is a national drug code that identifies in meticulous detail every single prescription drug in the United States. And that gets down to the packaging, the count, the size, you know, what strength it is, whether it's a caplet or a tablet. All of that stuff is contained in these national drug codes. And that's all publicly available information. So if you can, and this is a difficult thing about healthcare, is it's not something like, oh, I can just download housing price information and start building a model. There's a lot of all of this detail that you have to get over in order to start being effective with healthcare data. If you try to just do a one-hot encoding on the 100,000 national drug codes and throw that into a machine learning model, you're not going to get anywhere. You have to sort of understand these codes and how to use them. But the good thing is they do standardize a lot of what goes on. I talked a bunch about all this billing data. You might be asking, well, what about if I want medical records? What if I want actual, how would I do data science in healthcare if I wanted like the actual clinical notes taken by a doctor? These are generally not publicly available, and there are no good sources. There are generally no good sources. There are two notable exceptions, which I'll talk about here. The first is something called Mimic. And this currently has, actually, this is probably not current. I think there's a new updated version of Mimic, but there's 45,000 anonymized ICU stays. They're all from Beth Israel Hospital in Boston. This data set has been collected for the last 15 years. You do have to take an online training class and get sort of certified in research use of clinical data in order to be able to get access to this. But it's the kind of thing you can do yourself. You don't have to have access, and it is free once you take that class. That data has actual detailed clinical notes for all of these ICU stays. So you get actually every note that the doctor wrote, every note that the nurse wrote. And there's another database that's called EICU that you also can get access to with a similar set of restrictions that has 200,000 patient stays from a wider variety of data. These two sources, if you look at any machine learning paper on natural language processing in medical records, it will use one of these two data sources. Like I say 80%, I think it's probably 95+% of the papers use these two data sources. So the good news is if you want to do this, there's an easy place where you know where to start. This is the equivalent of ImageNet for medical records data. One of the tricky parts is if you actually want to put this stuff in practice, there isn't a lot of variation. You know, all of the Mimic data is from one hospital in Boston. And so this is something to think about when you get into healthcare machine learning. Is really the data is not super accessible. At Closed Loop, we deal with this data every day. Every one of our customers, we have a HIPAA compliant cloud. Every one of our customers deals with personalized medical records, and so we have a lot of security to deal and keep our customer data safe. But in terms of open source databases, these are the best options. A little bit more on the data. I think it's always important to get grounded well in the data. Healthcare data, generally, a couple things about it. Usually, I think the best way to think about it is as a non-uniform multi-valued time series. So you'll get a lot of different events, information and events that occur. Something like prescription records, for example, come in as a time series of this person got this prescription filled on this date. Another day, maybe it's a week later, maybe it's 3 months later, they get another prescription filled. So you get these kind of time series data that generally has a bunch of information associated with each time point, but they're all completely non-uniform. It's not like IoT data where you're getting readings every 5 seconds, right? If somebody doesn't go to the doctor or doesn't have a healthcare event, you often won't get data. Certain things like continuous glucose monitors do give off that kind of real-time IoT-like data, and certainly like in the hospital kind of medical device monitoring also does. So I'm sort of hand-waving some of this stuff. There's a lot of different data, but particularly what I'm talking about here with this $1 million challenge we did, it's sort of longitudinal data that works over years, and you get a very, very non-uniform time series out of it. One of the good news about healthcare data is it's generally self-labeling. So in terms of machine learning, because you have a time series, you can often look forward in time to determine an endpoint you're interested in. An example is if you want to see which patients are likely to go to the emergency room in the next 6 months, you have a time series where you can see what happens to that patient in the next 6 months if you look back historically, and you can use that. So that's a nice aspect of much of this healthcare data is you can use the data to sort of create labels. If you're interested in what happened to this patient a year from now, if you have their history, you can know that. You can often look back at multiple points in time for a patient and see what's going on. So labeling in these kind of data sets is often not a big deal. Now, if you're looking for something like using image classification for X-ray images or something like that in healthcare, then you do have the sort of typical labeling problems you have in other domains, but not always for a lot of this work with health records. I think this is a good time to point out that the thing that's different about healthcare is that the rows in your data set represent human lives. And I think this is really important. It is very easy to lose track of the fact that all this data is actually represent every one of these hospital visits is somebody who really had a pretty tragic event that went on in their lives. And personally, I feel that you're a better data scientist if you keep that in your head while you're doing all this work. If you abstract yourself too much from what's actually going on, then that's important. I have the questions up here. I may try to answer some of these as they come up. We'll see how that goes. But so this question came up about, have I seen any applications of reinforcement learning in healthcare? If so, what are they? I've seen some applications of reinforcement learning in research in healthcare. One of the notable papers was something that was people looking at sort of how to, for people that are in the ICU, understanding there's a lot of detailed titration that has to happen. If you're in an ICU, you can picture somebody in the ICU and they're hooked up to 4 or 5 different IV drips with different drugs, and how to actually tune the different drugs that somebody is being given in the ICU to best sort of move them through and get them out of danger. I have seen reinforcement learning applied to that problem, but never used in practice. I think it's a very scary thing, obviously, to turn over that kind of control or how that would even work. But I have seen some studies showing that, hey, if we used reinforcement learning to adjust these kinds of titration of different medications into somebody, then we could improve their outcomes. Those are, that's a tough. The problem is when you start with the ICU, it's always very tough to sort of. That's a tough thing to roll out, because when you make a mistake, somebody probably dies. That's probably one of the most notable ones. I've seen a couple others, but I don't actually know of any good ones that are going on in practice. Yeah, what are the ways in which data scientists try to remind themselves that the rows in the data are human lives? It's just a useful thing to remind yourself every once in a while. I wish I had a better. Well, actually, I do have a somewhat related thing that helps me. That story I'll relate here. It's actually, this was a case where the rows weren't human lives, but I did learn a lot from this event. This was something that happened to me back in 2003. I was actually I was working on the Human Genome Project, and we were predicting protein coding genomes. So nobody knew how many genes there were back then. Now we know there's about 25,000 genes in the human genome, but we didn't know. We thought maybe there's 100,000. We were trying to figure that out. I had written some algorithms to try to identify likely candidate genes. And then I was working with this biology PhD student who was researching the top candidates and and trying to figure out if they really were. So he would figure out what the gene would be if it did exist, and then he would devise a test to see if that was real, and then he would go search and try to find it. For me, I was just like, oh, I'm writing an algorithm, and I generated this top 10 list, and I handed it to this biology PhD student. That student had to go research those things, pick the ones he was interested in, and then design experiments, each one of which took like a week in order to do. And then I found a bug in my code. And one day I handed him a brand new list that was completely different than the previous list I had done, because my original algorithm had a bug in it. When I handed him that list, he just completely crestfallen. And I was like, oh yeah, sorry about that. I had a bug. And he was like, I just wasted like a month in the lab on these things that didn't pan out. And you know, when you have that kind of situation come up, it made me realize like, oh, it's very easy for me to rerun this algorithm and make a change and say, oh, I have a bug. But like when you hand those results to somebody and you say, here is what my algorithm came up with, you better be ready to stand by the fact that if you have a bug in there, you have to be ready to deal with the fact that you may have wasted somebody's time, and treat that person's time as much as you would your own. And so this is something I really learned in data science, because it's very easy in data science to tweak your algorithm and play around and generate a new list, but understand that if what you're predicting is a real thing in a person's life, and you're asking them to do something different based on your algorithm or your result, you know, are you really confident? Would you give that to your brother or your sister or your mom and your dad and go tell her to spend your time on that? It made me look for a lot more bugs in my code after that happened. And I'll talk a little bit more about this sort of towards the end of the talk, but I'll get back to this, because some of these things are subtle, but they're important. There's another question here about data sets for research in other countries. It obviously varies greatly by country. Outside of the USA, there are some very good data sets that I will say outside of the United States, almost all the data sets for healthcare are government controlled. And so getting access to them is a matter of dealing with the government of the particular country you're dealing with. That's sort of the nature of healthcare in most of the rest of the world. Probably the best known database is the UK Biobank. They have 500,000 or 1 million different patients with extensive detail, full genome sequences, all kinds of health history, really a lot of detail. So part of the reason I think Google acquired DeepMind in the UK, and they've done a lot of their healthcare work in the UK, is because of those databases. Great. So I talked a little bit about healthcare data. I'll get back to some more of that a little bit later, but figured I'd get into a little bit of a different topic. I want to talk a little bit about bias. This is probably bias and fairness is, of course, a very hot topic in any sort of data science and AI discussion right now. In healthcare, there's some very particular things going on. So there was a major lawsuit in late December or November of 2019 against Optum, which is a big analytics provider in healthcare. And basically that algorithm was using cost as a proxy for sickness. So it was trying to and this is a somewhat reasonable thing to do. It said, hey, people who spend more on healthcare are sicker. And so if you want to predict who you should be delivering resources to in order to improve health, find all the people who are really expensive. At first blush, that seems fine. What actually happens is that racial and socioeconomic differences in cost, there are very severe racial and socioeconomic differences in healthcare spending that are unrelated to health state. So different groups who are both the same amount of sickness might spend vastly different amounts of money on healthcare. And some of that is just because of the resources they have available. Some of it is the cost. If you live in a very fancy place, you might go to a very fancy hospital that charges more than a cheaper hospital. And some of that has to do with trust in the healthcare system. Certain groups have less inherent trust in the healthcare system and therefore are more likely to go with some kind of home remedy than go to the doctor. Which leads them to have lower cost, even though they aren't necessarily healthier. Optum was sued over this. One important thing here is that this is bias that is built into the data set. So it's kind of one of the most difficult kinds of bias to address in a machine learning sense, because the underlying data you're working with has the bias. You can build a model that predicts this cost in a completely unbiased way, but the fact is the data you're learning off of is biased. It's very difficult to get around that. The actual remedy was, instead of looking at cost, they looked at what we call utilization, which is what did you actually have happen to you? So instead of looking at how much let's take the appendicitis example, because I think I used that in an earlier slide. Instead of looking at how expensive your appendicitis was, they just look at the fact that you had an appendicitis and you had an appendectomy. That is a much less biased occurrence. You may find that certain groups it's much more expensive on average than in other groups, but the incidence of the underlying disease is a much less biased thing. And so Optum has since fixed those models so that they now work off of utilization rather than cost, and that's helped to address the issue. And so data set bias is one thing. Another important thing is just your model can be biased, and it's important to check that, have you brought in features that are biasing your model? As part of this $1 million challenge, we actually developed a new fairness metric. There was an article we read on that had 28 definitions of fairness for machine learning. We read through all that. And it was sad because we decided that the one we thought was most appropriate was not in there. So we created the 29th definition of fairness. I did not want to do this, but at the end of the day, it's important to realize that there isn't just a fairness is not an easy thing to just define. And importantly, the most common measure of fairness, which is called disparate impact, is almost always the wrong one for healthcare applications. I'll talk a little bit more on that about that on the next slide. But the one we chose was group benefit and quality, and it really looks at the predicted risk for a group versus the actual risk for a group. And this is important because in healthcare, you have very real differences in underlying disease susceptibility based on race or gender or sickle cell anemia it does not affect races equally. It affects African Americans, right? It's an African American predominantly disease. And so when you actually predict risk for these things, you have to not look at, hey, am I trying to equalize the risk across all these groups? You have to look at, am I trying to equalize the risk of all these groups relative to what their underlying risk is in the population? And this is a very critical concept, because the standard out of the box bias algorithms that most people will talk about, bias metrics for sort of loan applications, is not at all what you want to use. You know, if you use that metric and you predict sickle cell anemia, and you want an equal outcome of equal risk for sickle cell anemia across all races, that's going to massively be biased against African Americans, even though you know, that the little fairness metric you're using will say it isn't. So I think these are tricky issues. It's very new, and it's something that people are still working on. So we created these metrics, and the nice thing with the metrics we have is we measure it. It is susceptible to the fact that we measure the underlying risk from the population, but then we look at how we're predicting relative to that. So for a given group, are we under or over predicting their risk on average? If it's So this is looking by race. We were looking at, in this case, we were looking at how does the algorithm systematically over or under predict risk based on race. And this one, you can see, you'll never get this sort of perfectly 1.0 everywhere. But we were sort of mostly within our tolerances for some of these. And we looked at this for several different common attributes: gender and age, disability, and dual eligible, which is a fancy word for whether somebody's on Medicaid and Medicare. So these are a bunch of different algorithms that we looked at, just a bunch of different metrics we looked at across different classes to see if we could identify whether our algorithms had systematic bias within them. And there are no, you know, we created some standards for this. There are no sort of well-accepted standards for how bias is too biased. These are new discussions. I think they're important to have, and they're important to think about these and raise these about our models. But you know, this is really an ongoing area. And you know, a thought experiment I always like to leave people with on bias is really, I don't believe there is no single quantitative metric you can use for fairness. And I think the easiest way to think about that is think about a model that predicts health outcomes and ask the basic question: should that model include race? Should the model be incorporating race into that decision? Some people might instinctively say yes or no, like there's a correct answer. I think there is pretty clearly not a correct answer. And if you do this little thought experiment, like, well, if you're using that model as an insurance company trying to set health insurance premiums, I think there's a pretty clear answer. There's actually a legal answer in the US, which is you're not allowed to use race to set premiums, and you can't change those premiums by race. So we have sort of decided as a society that is not okay. However, if you're a nonprofit organization who's trying to help people out and you want to figure out who are the best people to help, who could benefit, then you probably absolutely want to incorporate all the information you can to figure out with the most accurate prediction who could benefit. And in this case, being predicted by the model as having higher risk is going to help you, not hurt you. And so the sort of ethical decisions around this changed drastically. And so should you include race in a model? Well, that totally depends on how that model is going to be used. And I think this is a very important concept, and it's what makes all this really difficult to talk about bias and fairness. I wish I had some more cut and dried prescriptive guidance here, but this is such a new area that I just think it's important that everybody be thinking about it and and realize that there's no simple answers of yes, always do this, or no, never do that, because you have to think about the ethical considerations of your particular situation. Yeah, is it legally legitimate enough not to treat data bias, but just give a thorough description of your data? I am not a lawyer. Don't take anything I say as legal advice. So I've disclaimed that. This is one of those things where I get back to like, remember that these rows in your spreadsheet are human lives. Like, so can you get away with it? I don't know, maybe, but like, these are people's lives. You're deciding whether this may be used to decide whether or not somebody gets healthcare. Like I think as a data scientist, punting to the, hey, I said what I thought the bias was, but I'm not going to take an opinion on whether this model is good or not. I don't think that's acceptable as a data scientist. You certainly can get away with it in some things. I think there's probably, I don't know that the legal standards are worked out very well in this case. I think, yeah, so I don't have a great answer for whether or not it's legally required. I think it is an important thing to think about. Yeah, once we decide to include race in our models, I'm reading another question here. What are the factors we need to take into account for the different races? Yeah, there are many. So underlyingly, access to healthcare changes, use of the healthcare system changes. So there are many aspects in there that can get rolled up. So even actually, if you don't put race in your model, many of these, if you put zip code in, but you don't put race in, then maybe you really kind of have encoded race in there. I think, so that the answer to that probably goes beyond the scope of what I can cover here. I think it's important this is one of the reasons I think it's important to use these kind of metrics where after a model is built, you sort of take the results of that model and interrogate it for bias to see how much of a problem it is. Because even if you don't put race as a variable in your model, you may find that it's biased for or against a particular race. And so, again, what these metrics are is after you've created a model and you have a set of predictions, you can sort of retrospectively say, hey, were those predictions biased? And so that's the approach we take, is take a look afterwards, see if you have bias, and then if you do, then go back and try to piece out where that bias is coming from and how to eliminate it, which there isn't always a short answer to. Great. So I guess the next, moving on from bias, the next sort of main topic I wanted to cover was the best way to communicate the accuracy of a predictive model. Yeah, the quick thing is, don't give people accuracy metrics. Show people what changes in their life if they use the model. What decisions are made differently, and how will that better decision help them? Here's a good example of, and all of these examples I'm going to show, these are all actual things I've done. So when I say how not to present this, I'm not presenting somebody else's work and saying they did a bad job. This is something I did that was not, that I look back at years later and say, I can't believe I actually presented this to somebody. So this was, we were doing a model to predict whether people would end up in the hospital after a knee replacement. So you go in for knee replacement surgery, you're supposed to do your physical therapy, and you're supposed to have follow-up visits. And then some people end up 6 months later needing some extra surgery to fix the knee replacement. Most of the time, that's because they didn't sort of correctly rehab the knee. They got scar tissue built up, and that has to be removed. And so we built this model, and we presented these results. We have all the typical data science things. We've got precision recall curves. We've got ROC curves. We've got percentage recall, everything you would want as a data scientist. What's your AUCs? But all these things end up, if you put them to somebody who's not a data scientist or somebody who cares about the result, they ask the same questions, right? Like, this ROC AUC is the number you tell me, was 78% good? What's good? No, like the last result you showed me was a 76. How much is 78 better than 76? Well, it depends. And then people will take this ROC AUC number and say, oh, that's how often it's right. So you're right 3/4 of the time. Well, that's not really what an ROC AUC is. Basically, all you've done is shown people that you know some math, and they don't really understand whether what you built will help them or not. So instead of having them ask you questions that you answer with "it depends" and "I don't know" and maybe sometimes, think about the questions you should be asking. So if you're building a model for somebody and you're presenting them results, the 3 most important questions I think to ask are always, what do you want to do with this model? Like, if I'm going to predict something for you, you want a prediction. What are you going to do with that prediction? In our business, the most common answer, and the one I'll talk to here, is, hey, we want to find the patients who are at high risk of some bad event, and we want to pay more attention to them. We want to do aggressive follow-up. If an example with this, with the knee replacement, is if somebody misses a physical therapy appointment for knee replacement, do you want to, how aggressively should you follow up? Maybe you text message them, but if they don't answer the text message, do you give a call? If they don't answer the first call, do you call a second time? Well, that really depends how high risk the person is of a complication. If it's somebody who really needs that physical therapy appointment, you want to make sure your nurse is getting on the phone and spending the time to get in touch with them. If there's somebody who's actually been doing really good and they're low risk, then okay, maybe they missed an appointment, it's fine. These are subtle things, but they actually end up being huge drivers of cost in healthcare. Because when you don't do those basic follow-up things and you end up in the hospital again, that's tens of thousands of dollars spent on an unneeded surgery. Totally available, totally wasteful cost. So what do you want to do with this model? How do you want to use the results of what you're predicting? The second question is, what do you do today? And people will often answer this, well, we don't do anything. And that's almost never the right answer. That people may not have an organized system. They want a model, but they're doing something today. So what do you do today? Find out what they do. That's the baseline. And then what does success look like? What do you, if you're putting this model in place, how are you going to decide whether or not that model is worth it or not, or whether it's a good idea? Any change you make, even if you're not charging anybody for the model and it's all free, any change that an organization makes has some sort of organizational cost associated with it. And so you'd want to assume things must be reasonably, there should be a notable improvement in order to justify making a change. And so these 3 questions, what do you want to do with the model? What do you do today? And what does success look like? I think these are essential in order to figure out how to communicate the results of the model. In this case, and again, I took all of these graphs exactly from historical things I've done. I wanted to show the good, the bad, and the ugly. I would never use this color scheme today. I'm not a good color person, but I've learned enough to know this is a bad one. Anyway, after my caveat, basically what we showed here is, with this knee replacement thing, is this is the same model, the same results I showed here, but the way we presented it this time was, hey, we can divide your population into 3 groups: high risk, medium risk, and low risk. The high risk population is only 13% of the people, but they represent over half of the admissions. They're 53% of the admissions. And then the low risk group is 36% of your people. It's a pretty good chunk, and they're responsible for almost no readmissions. These are people you can basically, you don't have to worry about following up on. Any work you're doing to follow up with that 36%, put it into doing better follow-up with the 13%. Rather than treat everybody equal, focus on that little red group. And then the middle group, that's about half the population, and they're responsible for a little less than half the admissions. Probably with that group, what you're doing today is going to work, is the right answer. So this told people, hey, here's what we can do, and here's what's going to happen. You can take all this work you're devoting to this 36% and devote it to this 13%, and that's going to help you out. And you're not you're not really worried about missing any of these admissions. This was something that when we showed it to them, they understood pretty immediately. Whereas the ROC curves and the other graphs didn't make any sense. And so on the side here, I've kind of just bashed ROC curves a little bit. So like, wait a minute, why is this the first thing I learned about in data science when building a binary classifier? If these things aren't good. And the answer is, well, first I'll give you just quickly review some of an ROC curve. I'm sure with data scientists on the line, many of you are familiar with this, but important things about the ROC curve is it's a curve that's looking as you sort of move a threshold along between any binary predictor. If you want to use it to make a decision, you need to sort of pick a threshold. An ROC curve allows you to take a prediction that's a probability and get a metric of accuracy that's independent of any particular threshold. So you sort of slide the threshold along and then draw a curve of true positives and false positives at each point. And then you look at the area under that curve. It's a great way to compare models to each other. It's independent of a particular threshold you pick, which is nice because often choosing a threshold is difficult. Another important thing to remember about an ROC curve, and I always like to remind people of this, is it depends only on the ordering of the predictions. If you took the probability of if you took a set of predictions, you doubled the probability of every single event, your ROC curve would be unchanged. As long as the most probable prediction stays the most probable prediction and the next one and the next one, as long as the ordering of all your predictions when you line them up is the same, you'll have the same ROC. And so an ROC curve doesn't guarantee, a high ROC doesn't guarantee that if your model says something has a 20% probability that it's going to happen 20% of the time. That's not at all what that metric is measuring. It's really measuring, if you line up all the predictions, how well do the distributions separate? I always laugh because they draw these nice binary distributions. These are often what distributions look like in real life when you draw these binary distributions. And so a lot of these problems they all look very easy when you draw the clean way, but in reality, there's a lot of tails and outliers in these distributions. And so, again, these things often look very different. And these are important things to understand. I think you'll see weird results sometimes, like, hey, this model looks like it's doing better, but it has a worse ROC. How does that happen? There's a lot of ways that can happen. And, looking in detail at your data can help with those. So again, are ROC curves and statistics useless? Absolutely not. ROC curves are a great way to compare relative accuracy of different models that are measuring the same thing. So if you have, and this is why they're used in all the academic papers. If you're doing classification on ImageNet or a variety of other prediction problems on a standard data set, it is a very good way to measure which is the better model. And it's very standardized for a binary classifier. Everyone knows what it works. Because it's standardized, there's just less bias in the interpretation of it. But some of the things they don't do is they don't actually tell you whether a model is good in an absolute sense. When I was in finance, if we had an ROC of 0.56, that was off the charts good. You can make a lot of money in finance if you can get a 0.56 ROC. If you're trying to build a vaccine and you need to determine whether or not it's going to hurt people, like a 0.98 is awful ROC. You need to be way, way better than that. So it's important not to get locked into what's a good ROC. All of these things are entirely dependent on where your model is used, what it's used for, and what the parameters are around. When you turn that model into something real in the world, a real decision, a real people, what kind of accuracy do you need? What do you do today? How good is the status quo, and how much better do you need to be? And RC curves also don't tell you whether your probabilities are correct. They just tell you whether the ordering of predictions separates the distribution. Couple more things. Some of my favorite things looking at ROC curves, they can be great for spotting issues. For this, this was a different model we did around different disenrollment. So we were trying to predict people who are going to leave a particular health plan. I built the model. I was all excited. I got a 0.89 ROC AUC right off the bat. But then I looked at the curve and I saw this. And there we go. I circle it in the next one. In this case, we were nearly perfect. So if you look at this, we had a false positive rate here of something, this is like a 1 or 2% false positive rate and a 50% true positive rate. So this means about half of all the people who disenrolled, we were able to get perfectly. I think if you're a naive data scientist who's just starting out, you probably get very excited when you see this. If you're an experienced data scientist, you're like, oh, this is wrong. I'm not that good. And in this case, there was some data leakage where one of the features we were using in the model was actually giving us clues about people who were going to be disenrolled. They had already disenrolled, but their status wasn't officially changed yet to disenrolled. We were able to find those people, and this was all just an artifact. And if this curve had been a 0.89 and it looked sort of more even, I would have been happier. But kind of seeing this clued me into immediately the fact that, okay, there's probably something wrong here. Either that, or there's some really obvious feature that we're able to take advantage. And if that feature happens to be a valid one, that's great. In my experience, if it looks too good to be true, it most likely is. And so with this disenrollment flag, again, we built this model. It could have the 0.89 ROC, but is that good? Even showing this to the customer we were building it for, they don't know what to do with this. They don't understand, okay, is this accurate or not? So again, I'll go back to these questions you should be asking. What do you want to do with this model? Well, they were like, well, what we want to do is find all the people who are likely to disenroll, and we want to call them and, try to get them, tell them about how great our service is, and basically try to resell them on this health plan. And we asked, what do you do today? And they said, well, we have this flag we use. I'm not sure where it comes from, but this one of our analysts created this flag, and it decides who we should go after. And we said, great, what is your success? What do you want to see? And they were like, well, we make a lot of calls right now, and we really would like to reduce that, make fewer calls, but keep our re-enrollment. We've gotten to the point that they basically gradually ramped up this campaign to improve their re-enrollment rates. And they got their re-enrollment rates to where they wanted, but they were spending way too much money in order to do it. And so they said, this isn't sustainable. We can't keep doing. And essentially, these are people who could be, working with helping people with pharmacy claims or helping complex patients or doing other kind of customer service tasks, but they were focusing on this re-enrollment. So they said, we'd like to be able to do fewer calls. So in this case, we built this graph. This is work I did at ClosedLoop. And we took that ROC curve and we drew it out for him and said, okay, given your current, if you make this many calls, and so this is the number of calls they made. So, and they had up to 23,647 members. So they, at the top end, they could have called everybody. And then we said, look, if you were to randomly call people, and they had 2,600 people who disenrolled, so a little about 10% disenrollment. We said, look, if you were to make 1,000 calls to random people, you would call 114 people who might disenroll. Your flag does better. If you call 100 people using your flag, you'll actually get 200 people who are likely to enroll. So if you call somebody who is, important thing is if you call somebody who doesn't ultimately disenroll, then that was kind of a wasted call. So you ideally would like to just call the people who are who end up disenrolling. We said, this is your current process. And then using a machine learning model with this accuracy we had, this is after I fixed that ROC issue. We could actually find 369 people. Out of 1,000 calls, more than a third of those will go to people who would have ultimately disenrolled. And that is actually more than you would get by making 2,000 calls at your current, at using your current process. And so here we were able to show them the number that they cared about, which is, hey, we want to make fewer calls. We showed, look, you could reach the same number of people roughly, or actually even slightly more, of the people you want to reach with half as many calls. This is not an ROC AUC, but this is very easy for them to understand and say, oh, okay, we can cut our calls in half if we use this model. Oh, that's a useful predictive model for us. And so again, we related to this to, here's what you want to achieve and here's what we can do. And I think this particular step is very, very important. Part of the problem we ran into is, okay, that's great. We were able to make these, have these discussions and get all this across. But those were like custom things. It was like, think about the problem, ask these questions, try to understand the decision, create some table or graphic every single time. That just felt like a lot of work and a lot of analysis to get right every time. So what we thought about was, hey, is there something we can do to try to make this more standardized? And what we looked is many of these use cases we were doing come down to sorting a list. It's all about, hey, I want to do this prediction of who's going to have this bad thing happen to them. And then I want to go tackle those, take the top end of that list and go tackle them. I think it's, so I lost my train of thought there. So it's important. So all of these are sorting lists. There's other kinds of there's lots of uses of AI models for many different uses. They don't all look like this, but for a category that looked like this, we tried to think about, all right, how can we standardize all those analysis? And the particular graphs, we call this is population health is the area we're in. How do you take a population of 50, 100,000 or 1 million patients and figure out who to direct what resources to in the healthcare system? So, and what we ended up with was this outcome capture graph, where at the bottom, we look at the percent of the population. And so we graph from the left side, the highest, the people most likely to have the issue, and then to the right side, the people who are least risky. And so if you are going to intervene on a certain percentage of the population, you can read that off in the x-axis. So if, and then in the y-axis, we put the percent of the total outcome. And this fits into something that is very natural for people in health, certainly in healthcare, to deal with. It's a very natural thing because people are used to, hey, the top 10% of the population are responsible for 50% of the costs of healthcare costs, or 30%, the top 5% of most sick patients are responsible for 40% of hospital admissions. People are used to that kind of logic, and they know that in healthcare. And so that's what we do. We say, hey, in this case, the top 10% of the population is, by our prediction, is responsible for 22% of whatever it is you happen to be looking at. In this case, I think it was readmissions. And you can compare multiple models here. So if you have, more than one model, the more accurate model is going to find more of the outcome with fewer people. Some of you may be looking at this saying, wait a minute, didn't you just draw an ROC curve? That looks like exactly the same thing. And that's very true. It took us actually a while to get to this graph, purely because it's so close to an ROC graph in a lot of ways. It turns out that if you look at the total percentage of people who had your outcome in a binary classification case, that's really the same thing as your true positive rate. And so we've really just relabeled the y-axis. And the x-axis is subtly different. So in our case, the x-axis is the percentage of the population that is being intervened on or that you're looking at. Whereas in the ROC curve, the x-axis is the false positive rate at a particular point. There is a very nice aspect to the false positive rate being the x-axis, which is that at a perfect model, we'll have an ROC, an area under the curve for this curve of 1. So if you never make a mistake, if you get all of your true positives without any false positives, you'll have a vertical line, and then you go over to the right as you add in the false positives. That won't happen in this graph, because you will always have to involve some percentage of the population in order to get there. So the area under this curve isn't always 1 for a perfect model. And so the x-axis is subtly different, but it's important because relabeling this axis and changing this to be a percentage of the population turns a graph that is incomprehensible to most lay people to something that we routinely explain to people and they immediately get. Hey, look, if you're trying to prevent readmissions, you could take the top 10% of your people, and that would account for 28% of the people who got readmitted. They can look at the graph, they can read the number. Oh, if you could intervene on more, here's what would happen. If you could intervene on less, here's what would happen. And so, I think this is an important point, is just because these things are close, don't mathematically, the mathematical focus is like, oh, they're almost redundant, let's ignore it. But this difference it's the difference between being incomprehensible and comprehensible to a layperson. I will say, as an aside, there are times when actually the ROC curve is exactly the right answer. If you were trying to trade off, if what you're trying to trade off is actually a true positive rate versus a false positive rate, an example of that is if you're, for sort of lab tests, if you have something that's sort of determining an outcome from a test, and you want to have a small number of false positives, because that's going to, every time you give somebody a false positive, they're going to have follow-on tests that are wasteful. And so the sort of total percentage of the population that has a true value isn't the important thing. It's how often do you give somebody a false positive is really the thing. So for sort of diagnostic testing, an ROC curve is actually the right diagram. But for many of these population health use cases, an outcome capture graph is the right answer. And so like both of those examples I previously showed with the pie charts and the calls, we would do all of these now with one standard graph that's very easy to plot. And so, one of the things we've learned around predicting accuracy, communicating accuracy. Another nice thing about this graph is because it's not true positive rate, it's just percent of the total outcome. We can actually use this same graph for continuous outcomes and regression, a regression type model and continuous outcomes, as well as a binary outcome. So if we're trying to predict total costs, it fits in this same graph where we can say, in this case, 13% of the patients are responsible for 41% of the cost. And you can know that up ahead of time. So it's useful once we educate customers on what this graph is. It's nice that they can use it whether they're predicting costs over admissions. A lot of times, as a data scientist, you think, oh, that's a continuous versus a binary outcome. Those are totally different. To a healthcare practitioner, that seems like the same thing. Costs and admissions, they're pretty similar. Why do you need a totally different kind of graph to look at one versus another? So this has helped us a lot. So this is a graph that we built, and I have a blog post on it minor variation on an ROC curve, but really we found it to be remarkably effective at communicating the accuracy of these results. Another thing we do, and this works on either of these curves, an ROC curve or a decision rule. Oftentimes when you're comparing a probabilistic model versus the status quo system, often the status quo will be some kind of hard-coded rule. So you might have something like, oh, we find everybody who has had 2 or more emergency room visits in the previous year, and those are the people we call high risk. Anytime you get a rule like that, you have something where instead of getting a probability, you're just getting a true-false decision. You basically only you have a dichotomous outcome. So given that true-false decision, you actually can compute the false positive rate and true positive rate for that. So whenever a customer gives us a hard-coded rule, we will draw that as a graph, as a dot on the ROC curve and say, look, this is the process you're using today. It has a certain false positive rate and true positive rate. And essentially, if we were to draw it as a full ROC curve, you know, assume there's a flag that you've put on all your high-risk people. Your ROC curve would essentially be a straight line from 0, 0 to this point. Because if all you have is the flag, you would just sort of randomly choose people among the people who have the flag. And so if you randomly choose, you would get a straight line from here to here. And then you would get a straight line from this point to 1.0. And so you can take something that is an existing decision boundary and plot it on a ROC curve. And this helps people understand that 2 things. First, it can help them to understand that, oh, this predictive model is more accurate than my existing model. And it can be more accurate because I could predict the same number of people and find more of the total event, or I could have a lower false positive rate and find the same number of true positives. And so it's often hard for people to, when you have a probabilistic result, you don't have to assign an explicit threshold. You sort of get a rank ordering and you can choose how many people you want to go after or choose where your boundary is. And this, I think this visually helps people understand the difference between a line where you get to choose the boundary and a dot, which is a fixed boundary. And so this is something we use. And again, you can plot this on either the ROC curve or the outcome capture curve. And again, it just helps to people to ground what they're used to seeing, which is maybe a fixed decision rule with a probabilistic system. So I've talked about all this graph, but ultimately, you know, people usually want to know, well, how is this going to change my life? That's great that you can predict this percent with this percent of the population. But one of the things we've looked at is, can we do better? For many of these predictions, we actually have in the closed loop, a return on investment calculator. And so this is actually something we do with, where basically we have people enter in some basic properties of what they're doing. How big is your population that you're going to use this prediction on? If you're trying to avoid some expensive outcome, what does that cost? The intervention you're doing on these people, how much does that cost? How effective is it? There's some simple parameters people can come in, and then we can turn that into something that dollar savings for them. And we can optimize and say, hey, here's how the optimal way of using these predictions in your environment. These are always a little bit of a hand-wavy calculation. People generally don't have these numbers. Some of them are difficult to get, and they're often, they don't often have them quantitatively, but this is a simple tool we use that let people play around where they can put in different assumptions and see what it results. And then figure out, okay, with a model A versus model B, how many more admissions could we avoid? How many more dollars could we save if we had this model that has a 3% improvement in ROC AUC? How much money does that translate into it? And I think trying to get all the way to there ends up being a very important part of communicating the accuracy. And this is where I think you really need to get to. And, we try to standardize these things as much as possible. Obviously, the further you get towards trying to do this, the more specific to the use case you end up being. And so you're not in the sort of pure data science world of every binary classifier looks the same. But your job as a data scientist isn't to build a binary classifier. It's to help somebody make a better decision. So I talked about some of these, the parameters that we put in. Again, people can change these, and then we use those to compute the ROI. So a couple things I wanted to finish up with. Useful features for healthcare models. So people are probably like, wait a minute, I'm healthcare. I try to build machine learning models for healthcare. This guy has told me nothing useful yet. So I thought I would share some of, hey, here are the things that just work. Hopefully if you're building machine learning models for healthcare, you're probably using some of these already. I give you some guidance on, what are probably the next best things to try. I think I have a better version of this slide. Yeah. So simple features, gender and age are absolutely essential in anything with healthcare. Age is the biggest single factor affecting healthcare, especially if you look at a large enough age range. Age is the dominant factor. Old people have more health problems than young people. Anybody who's older will be able to tell you this. Basic counts and indicator flags are extremely useful. So how many times has somebody been to an emergency room? How many days have they spent in the hospital? All of these kinds of basic counts, these are utilization counts. And there's a ton of different ways you can do these. How long has it been since you've last been discharged from the hospital? There's a million variations on these things, and they're very valuable. Indicator flags are very useful. I talked a little bit about the 70,000 ICD-10 codes earlier. There's a whole discipline of medical informatics that really is about extracting useful features from all kinds of medical data. And so an important thing is don't necessarily try to go this alone. If you try to build these models, read some papers. There's a lot of really good features to be able to do this stuff. For diagnosis codes particularly, there's something called the CCSR categorization. I've got a link to it here. I think that CCS was an older version of it, but it is a categorization that divides up all of those 70,000 diagnosis codes into a much more manageable set of 500 or 600 different diseases. Just throw flags of those things into a model, and it will do decently well at predicting. A model that just uses diagnosis codes, some of these basic counts, gender and age, will outperform almost any handcrafted rule that people come up with. It's just a pretty simple thing. Another important thing to think about when you're building features or doing healthcare data science, it's important to distinguish nothing happened from no data. So, and what I mean by nothing happened is positive assurance that no event occurred. And that's different from not knowing. So if you have somebody, if you're working with a hospital, hospitals will often only get the data for procedures and events that happened in that hospital. If the patient went to the hospital next door, there's no record of it. Insurance companies are a little bit different. Insurance companies generally, if somebody's insured by a particular payer, then that insurance company is going to find out about everything that happens to them. You may find the same event, but depending on who gets it, you need to think about it totally differently. Because if you're dealing with a hospital data set and you haven't seen this person in 6 months, you can't make the assumption that that person hasn't been to the emergency room or hasn't had something happen to them over the previous 6 months. You just know that you haven't seen it. Generally, when you see that something happened, you can trust that it did really happen. But you need to understand whether the lack of an event of information about the lack of any information, is that nothing happened, or is that you may not have the information about what happened? And so with insurance companies, it's important to know when a person was covered. If a person had a 6 months lapse in their insurance, you may see a gap in their medical record. That doesn't mean that was a period where they had nothing happening to them. That means that was a 6-month time where they had a gap in their insurance, and now their insurance company doesn't know what happened. That can be you can come to a very different conclusion based on what happens there. And so it's an very important thing to consider in healthcare. This happens in other sort of observational data sets. But I think it's particularly bad in healthcare, especially when you're dealing with like a hospital or a doctor who only gets a very limited view. And that's something that's changing, certainly in the US. Medicare, a good example is Medicare. If you're a doctor treating a Medicare patient, Medicare is actually setting up an API that will allow you to be able to get that patient's medical history from Medicare so that you can properly treat them. That was supposed to get rolled out earlier this year. It's got delayed because of COVID, but the plan is still to get it out there. So that's something that's getting better, but still a big deal. Those are some of the simple things that work. And I would say until you've done all of those, don't even look at this page. There are many other features that are relevant, some more relevant for different problems. And really at Closed Loop, this is a lot of what we do is pulling all of these things from the research, doing very good, solid implementations of them and making them easy for customers to employ. Procedures and drugs. So I talked about diagnosis codes. That's definitely the place to start. But there's a lot of information in drugs. If you understand that somebody's taking statins or they're taking insulin, you may not have a code that says they're diabetic, but if you know they're taking insulin, you can guess that they're probably diabetic. So much of this information helps to reinforce. Some of the other ones we've used that are very important, the frailty index. You can go search this on Google. I don't have the link here. But it really looks at things like the diagnosis you've had. Have you had any durable medical equipment? So are you on oxygen? Do you have a wheelchair? And it kind of gets an overall view of frailty, which is maybe a qualitative, it puts a quantitative assessment on a generally qualitative condition that a person has. Medication adherence is another great one. So the primary way you do this is you monitor people's prescription refills. If you're getting prescription data, you can monitor the refills and see, are they getting a 30-day prescription refilled every 30 days? That means they're probably taking their meds every day. If they're getting a 30-day prescription refilled every 60 days, that means they're probably taking their medicine only about half the time. And so that can give you an idea of, are people really taking their medicines? Geolocation matters. So we can geocode. So just where you live in socioeconomically does have a significant amount of impact on your overall health state. People live in food deserts, or they live in nice areas with good access to healthcare. Those things matter. And just how far you live from the nearest hospital or emergency room matters. There are fancier ones we do. Treatment-resistant depression is one where you can look at a combination of somebody's diagnoses along with what they're doing in order to treat it. And if you see somebody switch drugs a bunch of times, that means they've probably got uncontrolled depression, and that is usually associated with worse self outcomes. So those are some of the fancy ones. And then there's a lot of social factors data that you can pull in. So the CDC has data, there's census data, food deserts, the walkability index. These are all information you can pull in to try to get more information. These kinds of things will easily double. Just from these last two slides, you can get 2,000 plus features on any individual patient. And this is without getting into anything sort of really fancy. This is basically all main published research. So how does all this stuff work? It's a little bit of an eye chart slide, but this is a slide we did on our that $1 million challenge we're doing for the Medicare data set. What we did is we looked overall at the models we had built and feature importance for those. In this case, it was SHAP scores that we used in order to determine feature importance. And we looked at, this model had 636 features, so sort of on the lower end of all the data we had. Part of that was because the data is anonymized, there's a bunch of stuff we would normally have that we couldn't use. There was no drug data, for instance. But one of the things we found interesting in this was sort of where did the signal come from at the end of the day? We found, demographics, your basic age, gender, where you live, that was almost a quarter of it. So there's just very little information there, but some very basic pieces of data are significantly associated with risk. Somebody who's 95 is just riskier than somebody who's 35. Your diagnoses, these were the two main things I said that were the first things you should go look at. You can see that's probably 45% of our overall signal. So that's, and then claims utilization. So see, these are some of these counts about how well you've been inpatient or not or whatever. And so you can see that's probably close to 60% of the overall signal. So you can build a pretty good model, sort of 60% of the overall signal with some very basic features. Of course, if you're looking at this in terms of human health and trying to treat people the best you can, you want to squeeze everything you can out of that model. So we had a bunch of these derived features. These things are things like frailty or treatment resistance depression, these sort of detailed specific features that go in that. They were responsible for about another 15% of our signal. Cost was useful for us, around 7.7. Social determinants, so do you live in a food desert? That was more. And then this model also included some environmental data. So we looked at air quality, weather, did you have a hospital admission? Were you released from a hospital admission for maybe asthma on a day when the ozone levels were really high? And maybe that's not a good idea. So, those signals did make the model. They're a small portion, but they did end up adding some lift to the model. So, this kind of gives you an idea. You can do pretty well with some very basic stuff, but if you get fancy, you can definitely add additional signal. I talked all about these features and feature engineering, and the obvious answer is like, wait a minute, nobody actually does that anymore. Everybody just uses deep learning now. Google published a paper in Nature that was very high profile that said, oh yeah, you don't need to do any of this. All you do is take raw healthcare records and throw them in, and deep learning solves the whole problem. So that Google did write this paper. It is an exceptionally well-written paper, and it's wonderful, wonderful research. So I don't want anyone to get the sense that I'm not impressed with what they did, but I think there's a few things you could probably look at. The baseline that they crushed was a very simple linear regression with basic features. It was not a XGBoost or a fancy machine learning model using a wide variety of features like I described in the back. Again, sort of imagine doing a linear regression on this little bit of the 60%. That's basically what Google baselined against. So it was a pretty easy baseline to beat. Their final model that they published in this paper was actually an ensemble of 3 models. 2 of them were deep learning models, and one of them looked an awful lot like XGBoost. It was a boosted tree implementation that was custom to them, that was very, very detailed. They don't actually say, they never published the individual statistics of those 3 models to say how well, these deep learning ones that just learned everything raw from the data, how well did they do versus the boosted tree? My assumption is, I imagine if the deep learning ones had done great by themselves, they may have just stuck with that. But I don't really know. And the other thing is, this is a Google research paper that had 35 authors. So yes, they got a good result. And they managed to do it without any feature engineering, but it took 35 authors to do it. Again, this was great research, but in practice, day to day, if you have a small team and a reasonable computational budget, sort of a little bit more old school deep learn, a little bit more old school, like build your own features. By old school, I mean like, do things from 2017 and stuff. These models still work really well. We've done a lot of work with deep learning, and I think it's very promising. And I do think you can get results that are equivalent. I don't think it's that traditional machine learning works better for these problems, but I don't feel like deep learning has consistently outperformed traditional machine learning sort of in this space. I feel like they're from our experience, they're very close. And you can get some better results with deep learning, but it just takes a lot more work to do it. And so I don't think feature engineering in healthcare is quite dead yet. The other thing is, in the feature engineering you work with in healthcare, there's been a lot of work done on that for a long time. Although in computer vision, there had been decades of work on feature engineering also that all got wiped away in 2 years. I don't think that's what you're going to see in healthcare. We're not just going to throw everything out and start doing all deep learning. At the same time, for certain problems, if you're looking at trying to predict heart arrhythmias from EKGs, like that's just a good deep learning problem. Where the data is standardized and you got a good time series data and you get enough data, I think there's a lot you can do there. Great. I want to finish with my last data science voodoo. And what I mean by this is data science is like voodoo because it only works if you believe it works. This is a really important point. You can build models, you can do all this stuff, but if you don't actually believe in it enough to trust it when it's telling you counterintuitive things, it is not useful. A great example I have, this is not a healthcare example, but it's one of my favorites. I was consulting for a company called Bluefin Labs. This is back about 10 years ago now. And they were a social media analytics company. And they were basically reading all of the Twitter. They were basically taking in the Twitter fire hose, aligning it based on advertising that was going out on television and trying to figure out what people were tweeting about ads as those ads were happening. So this was very novel stuff in 2012. Bluefin did an analysis for Coke at the London 2012 Olympics. There was this custom campaign they did right down here that you can see. You probably don't recognize that ad because they never actually ran it, or they didn't run it very much. Bluefin did this engagement. They said, look, the sentiment on your new campaign is maybe a little bit positive, but we're actually getting better engagement using your traditional ads. I forget which ads, but it was kind of their recycled, kind of more standard ads, and not the whole novel campaign they had come up for London in 2012. So Bluefin was a bunch of data scientists who present these results. And then, the Coke executives are saying, hey, you're telling us we should replace this ad campaign we spent tens of millions of dollars creating is not doing as well as as what we just running our regular ads. So here's the moment. Here's the moment where, like, do you actually believe in the data science you did, or were you just doing a bunch of numbers? Because if you're doing a bunch of math, you're like, oh, I don't know, you paid a lot of money for that. Probably you should run those ads. But if you really believe in the data science you're doing, if you really think you did the right thing, then your answer is, no, we think this is the right analysis. You should scrap that whole tens of millions of dollars campaign and run regular ads. If you're not willing to do that, then you probably shouldn't be in data science. That's my feeling on this. If you're not willing to stand behind the results you say and tell people to do something that is counterintuitive and different, then really it's going to be very hard for you to make a difference. All you're going to be able to do is tell people things they already know. It's always easy to get people to believe when you confirm their existing bias, but the real value comes from when you challenge people's biases. Of course, you have to be right. In this case, they did a very good job. They were confident in what they did, and all worked out well. I guess we'll never know in this case. In this case, we'll never know. But there are another story I want to give. Again, not a healthcare one, but relevant, and I think it's important. This was an automated trading system I was running. We were trading on the S&P 500. I was running a hedge fund at this point. I was doing 3,000 plus trades a day, so not super high frequency, but kind of a lot. It had a Sharpe ratio of 3, which was reasonably good. This was a system being traded live every single day. We had real money on this. For full disclosure, this is not the original graph. It's kind of similar, but I could not actually find the original graphs of the performance of this system. But this will illustrate the point. So over a 5-year back test, this thing had done very well. Wasn't positive every single day, but did have a lot of positive time. And so we had been running it. And the investor we had who had been fronting the money was very happy with it. We had 1 week that was our worst week ever. They shut us down. The investor told us to turn it off after Thursday. But it was the worst week we had ever had. It was just some days of really bad results. Other days, it was down every day. Some days worse than others. The investor said, "Hey, turn it off Thursday afternoon, shut it off. Come back to me on Monday and let me know what you want to do." So we spent most of that weekend digging in, trying to figure out what was going on, looking at all the statistics, running all these analysis, trying to understand. We didn't see any bugs. We looked at obvious outliers. There wasn't a day that was horrible. There wasn't a stock that was a particular outlier. It was any individual day was not the worst day we had ever had, but they were kind of all strung together. Any individual stock wasn't the worst we had ever lost on that stock, but they were kind of all kind of bad. It was the worst week we had ever had in backtest, but it was only 2% larger than the worst one. So it was just slightly the worst one. We did a ton of analysis on this. And it was a lot of statistics, like trying to get very convinced. The response we ended up with, and you'll see right here was that bottom point. This is the point where the investor came to us and shut us off. We went back to the investor and said, "We've looked at all this. We got unlucky." And that was our explanation. We said it was a bad week. We got unlucky. We think if we turn it on Monday, it's going to do just fine. Nothing we saw convinced us that this was a statistical anomaly or that the system was operating outside of its boundaries. It just looked like we have, at some point, you're going to have a week that's your worst week, and it happened to be last week. This was a really hard thing to say. It would have been easier if we had found a horrible bug in the system. It would have been easy if we had found something. It would have been easy to say, "Hey, let's turn the system on, but cut it down. So we're only going to invest half as much money until we see that it's working again." But we told them we wanted to turn it on full. It was a tense discussion because we didn't have anything other than statistically, we believed this was within the realm of possibility and was the most likely statistical answer is this was just an anomaly and we'll be fine next week. So we turned it on at this point. This is what happened to it. It ended up being, very, very good after that point. And it was just, it happened to be our worst week. It was just bad luck. And this was an important point because, you have to understand what human biases are. You want an explanation. When something goes wrong, it's easy to think about a random sample in a abstract way, but when you when you're living that system day to day and you see a bunch of money getting lost, you want an explanation. It's hard to you have a natural bias for those, and so you have to sort of have that bias in your head and be able to correct for it. And this is where being abstract and statistical helps you avoid those biases. So I spent most of this talk telling you about how you can't just live in the statistics world and ROC curves and not think about the context of the system you're using. But now I'm going to sort of flip it around and say, we had to take ourselves out of the context of the system and turn it into an abstract statistical problem to get away from the biases in this case, in order to understand what we want. And so, part of this is that like all the value in your results are in the counterintuitive ones. All the cases where you do a bunch of data sciences and it confirms what you already know, it makes you feel good, but it doesn't actually improve things. The interesting things are when it's a counterintuitive result. So you got to focus on those. I said here we understood our biases. I will always recommend these two books, Thinking Fast and Slow and Nudge. These are great books on behavioral economics, which ultimately, I view behavioral economics as the study of the biases we have in decision making as human beings. That's my definition. I just made it up, but I like it. And I think the more you can be aware of what the natural biases are, identify them and help them, that can really help you spot those biases in people you're talking to, and probably most importantly, spot them in yourselves. And so again, just to summarize, I want to cover the two big mistakes that I think people often make. And one of those is relying too much on statistics, thinking that an ROC curve is the be all end all to accuracy, forgetting to relate the data you're doing to real world things, not working with whoever is using the model you're building to understand how it impacts them, and not doing extra legwork to sort of understand how, get beyond the traditional statistics to understand how do you put a problem in context. And then the other one is exactly the opposite, right? Not believing in statistics, being biased, not being able to separate yourself from the problem, or not being able to trust in your models enough to believe in them when they tell you something counterintuitive. And it's important. I say this here very cavalierly, like it's hard to there's a reason it's hard to trust things that are counterintuitive. It's because they're often wrong. Most of the time when your model tells you something counterintuitive, it's probably because you have a bug in your code or you made a mistake. And so, it's not, it's just that it's important to dig down and understand, is it really a mistake or a bug, or is it actually something counterintuitive? If you say, oh, it's probably a bug in the code, I guess that thing didn't work out, you have missed an opportunity for something potentially really interesting. But you also have to be prepared for the fact that, 80-90% of the time that is what happens. So, these are sort of my existential thoughts on life as a data scientist. I think that's, yeah. I think that's it. There's a few questions here. I can sort of go through some of these in the chat and talk about them. We've got a few minutes left. So which ML algorithms do you recommend mostly to start with? Do you recommend any special treatment for imbalanced data set in healthcare? It depends what you want. So there's sort of like linear regression works very well for very basic explainable models. Personally, I sort of will do a linear logistic or linear regression for a basic model, a regularized version of that. And then usually XGBoost is my kind of workhorse machine learning model. It does very well out of the box on a very wide variety of problems. And about imbalanced data sets, XGBoost has the parameter where you can tell it to weight the, you can basically give it a parameter to reweight the classes internally, so it will work harder to get the correct, it will work harder to get the imbalance, the lower probability class. And so we found that works. That's basically the main thing that we do for imbalanced data set, is just making sure that I forget the exact name of the parameter, but the weighting the training samples. And I think it's a weight parameter that you set to sort of 1 over the frequency of the less frequent class. An important thing, if you use that parameter, it will make your model uncalibrated. So the probabilities you get back will not be they won't be the actual, like, because you've made the rare event more frequent, the probabilities you get back will be much higher. So you'll get back a 0.5 probability for an event that occurs 1 in 1,000 times. There is a rescaling you can do. You can kind of Google that, but you can rescale back the probabilities, and then you'll actually find that XGBoost will often give you a very well calibrated curve as long as you do that rescaling. So that's one of the things we do. Let's see. Can you talk about the fine line between politics and data insights facts? Wow. That's a very relevant topic. Yeah, I mean, there is a lot of I find a lot of so many statistics being abused in the and by sort of everybody. I think people like to throw around facts and statistics to support their arguments, often in ways that don't really, when you dig into them, don't really support the argument that's being made. And I also think conclusions in data scientists are often much fuzzier than they are in real life. I mean, just that, you know, the obvious one being hydroxychloroquine that I can think of right now. There is the evidence is not overwhelmingly that is a horrible approach to treat early stage COVID. It is also like overwhelmingly not that we should be doing it. There is kind of, I think from and now I'm probably stepped off some cliff here, but you know, I think a recognition, I would love to see more of a recognition that, hey, like, there's a lot of things we don't know, and it's worth like the idea that something might be worth studying to see, and we should be trying it a little bit. But, you know, I feel like if data science can help make things a little less black and white, that's what I would love to see. So people acknowledge that it's not that this thing is either horrible and going to kill this drug is going to kill everybody who takes it, or that it's completely ineffective, or that it's like a wonder drug. Maybe it's just kind of messy, and maybe it helps a little bit in some cases, but other people have side effects. And some particular discussions I've had around, I get asked a lot of statistical questions by people trying to interpret the news. I think it's important as a data scientist to be true to the facts and try to, not everybody has the analytical training to really go in and assess quantitative things in detail. And so I think it's important for those of us that do to make every attempt we can to pay attention to the real data and not buy it, you know, as much as you can, try to do your own analysis. I think that's as much as I'll probably go in on that one. Will I be posting slides? Yeah, I can post these slides. I can do that. Let's see. The data science I believe in is more causal inference. I love causal inference. I've done a lot of work in causal inference. I think you can believe in all of it. I think there's a lot you can do with correlations that work pretty well. I think the biggest danger of correlations is not realizing they're correlations. If you, and we walk a fine line with this, people often want to treat, we produce SHAP scores for our model. People often want to treat those as causal. And in many cases, they kind of seem like, in many cases, there's a very plausible causal explanation and people will immediately jump to that. And so again, that's a bias you have to be very careful of. I love causal inference. It's also not always the easiest thing to do. And so I would love to see it used more. I would love to see it taught more. I agree with you there. Let's see. I think I read through. Should we have insurance coverage to encourage adoption of machine learning? Insurance coverage to encourage, I can't quite understand that question. Yeah, any other questions I can answer? There's a few other ones. The red, yellow, green, that thing is just, that's a very jarring picture. I think a lower, red, yellow, green isn't necessarily bad. I think it was just so high contrast that it distracts in that. I think a more muted classification would have worked better. And the obvious colorblind issue. How do you link bias with problem, e.g. multi-class classification versus binary classification? Yeah. You know, that's a, the metric we did around binary classification because that was the problems we had. I think you could think about how to extend that. I think the same way you kind of extend, you know, F1s or something to multi-class. I think you could probably do similar kinds of things on bias there. I haven't personally done that work. And again, bias is so new. It's still something I think people are working on. Whew, that's a lot of talking to like 2 straight hours. I hope so. I think, you know, my email address is there. Happy to, you know, anybody who wants to connect with me directly, LinkedIn or email me, happy to chat. I think we'll post these slides and yeah, thanks everybody for coming.
All right. I would like to thank Dave DeCaprio for his valuable time in this awesome presentation, and would like to thank everyone who had become a part of today's speech. As Magnimind Academy, we are organizing a lot of events and programs like this. You're always welcome. We have a lot of free programs where you can check from our website, magnimindacademy.com. And thank you. Have a nice day.
Thanks.